Well, thank you for coming to our session. My name is Alisher Maksumov. I'm one of the architects for GE's industrial platform called Predix. So let me start off with this picture. What do you think this is? Any guess? Exactly. So this is a blackout. So in August 2003, there was a major blackout on northern east side of the U.S. and impacted also Canada a little bit. So about 50 million people lost power for almost 2 days. And this blackout caused 11 deaths for various reasons. Also, it cost $6 billion to the country, damages. So it was major. It was the largest single blackout in U.S. history. What happened? So according to researchers later on, they found that one of the high voltage power line went off, and the system didn't alert the operators what happened. They didn't know what happened for several hours. They tried to figure out, and the impact cascaded to other power lines, and that took down the entire system. So after that time, government issued stricter regulations. They said need to upgrades and things like that. So think about it. Single blackout caused this. And we have so many blackouts every year. The power grid is the largest network in the world. Okay, everything is connected. Everything that uses electricity is connected to it. So now, with the regulations, with so many companies trying to improve that, still not reliable, right? So now, what about this? When we talk about IoT, right? By major research organizations that keeping track of different technology trends, predicting that by 2020, we're going to have about 25 to 50 billion devices that will be connected to the network. Okay? Think about that. What's going to happen? We'll have no regulations. We don't have a single operator responsible for everything. We'll have all kinds of different devices with different capabilities. We're going to be in complete chaos, right? So that can cause some inconvenience, because when you talk about IoT, typically people think about home appliances. Some of my home appliances are now connected to the network. They have some smartness built into it. I can control my lights from my cell phone, right? So I have a few devices at home that can control my lights. But sometimes it doesn't work. So I click something, nothing is happening. What happened, right? It causes a little inconvenience to me, but then there's no major damage. What we're talking about here is basically the larger things. I don't even want to call them things. That's why GE calls them, these are, large assets that produce something, that produce value for us. So we're talking about turbines that generate power. We're talking about gas compressors. If you came to this room earlier, when SATURN was talking about, they talked about compressors. We talk about big MRI machines, jet engines. Everybody flew here, right? You were flying in one of the aircrafts that had GE-built jet engine. We're talking about locomotives that carry cargo. So these are the large assets that are operated by some companies, some operators. And they produce enormous amount of data. So our market research found that by 2020, the market of the industrial IoT or industrial internet, what GE calls it, is going to be larger than the consumer IoT, or for that matter, than the enterprise data center world. Okay? So now, let me give you one example of how big that asset is, right? So this is a gas one of the gas turbines. It weighs about 1 million pounds. Okay, it has 6 major sensors that produce 8,000 data points a second. So imagine you have hundreds of those or thousands of those. They don't stop. They operate 24/7. They constantly generate large volume of data. They need to be operated safely. Okay? So what problems we're trying to solve with the industrial IoT? So this is kind of an image of a power plant. What we're trying to solve is we want to reduce unplanned downtime. What does that mean? So the asset is utilized fully. It doesn't stop because we need electricity all the time, right? We can't take a break from it. We have so many devices now. Okay, so the biggest problem is how do we build a system that helps us reduce unplanned downtime? Not easy job. Safety, okay? The people, humans are working around the assets. So it has to be safe. Maintenance. So assets need to be maintained. But how do we optimize when you have multiple assets, not just one? And efficiency. So we want to get as much as possible from assets. So now, how do we design such a system? So we need to look into key capabilities that system has to provide. And those are, and I'm only mentioning a few of them, connectivity, right? Number one, so all the assets need to be connected. So we need to get data, constant stream of data. We need to know what's happening with the asset. We need to be able to see the assets, okay? The topology, how they connected, what's happening. Because now, the corporate world becoming ever global. So we have assets distributed globally, not only in one continent. We want to be able to manage assets remotely, okay? Manage software, be able to, apply some kind of analytics, predictive algorithms that tells us if something is wrong with the asset or something is about to be, wrong in the future at some point. So we need to know that. And you need to be able to be alerted. Everybody carries one of these. If you can get alerted on time, we can take appropriate actions on time, okay? So that's the problem we're trying to solve. So now, this sort of shows the architecture design goals. So it's a full spectrum. So we can't just, so a lot of, platforms out there today, software platforms, they focus on either this side or that side, okay? That side is industrial cloud world. Everybody has something in the cloud today. There's a few major cloud, infrastructure providers. You either use those or you build your own. We'll give you, infinite storage, compute, and all what you need today to building modern software, right? On the other side of the spectrum, you have assets, large, small, and you have software that manages these assets. But then there's the line between the assets and the infinite compute is not straight line. There's lots of hops you go through. And anything can go wrong. So you look at the sensors, controllers, SCADA systems, historians that collect data, gateways, and such. So many different devices, all kinds of different software in between, okay? Anything can go wrong. What do? So we need to account, we need to look at the holistic picture, account for everything in order to design the right system, okay? So some of the design goals, system has to be responsive. If anything goes wrong, it has to take care of it before it goes into the cloud. Otherwise, it's going to be too late, or something can blow up, causes huge damage. Interoperable, because we're living in the manufacturing world where you have all kinds of systems, legacy systems, new systems. They talk different languages. If you think about the data acquisition, there's so many different protocols, hundreds of protocols, literally. So we need to be able to interoperate, understand, and get data from all kinds of protocols, okay? Fail-safe, safety. I cannot emphasize, enough about safety. Remotely manageable. So today, not all the systems remotely manageable. So whatever we build needs to give us that capability. It's one of the, important capability, because otherwise, the systems, once the customers purchase large assets with software, they stay there for decades. If you want to be able to upgrade, think about security. If there's a flaw, security flaw in your software, if you don't update it on a regular basis, something bad can happen, okay? So scalability, we understand that. So lots of data, we need to scale infinitely because more data coming. System always has to be available. Otherwise, just like my first picture, Blackout, we don't get alerted, it's not available, we don't know what's going on. Easy to use is a very important thing because everybody got trained now on the phones. You point and click, you move things around, so easy, so intuitive. Why not design industrial systems just like that? Why do I have to have this complicated design that only certain people can learn and stay there for the rest of their career, right? So things changing so fast nowadays. So our approach is basically there's lots of, information here, but just to point few infrastructure. So we need to have a cloud-hosted infrastructure that scales. We need to adopt modern software engineering because not only the system has to scale, but also software development has to scale. You can't have like 3 or 4 guys sitting and writing industrial software. It has to be, first of all, it's too big for 3 or 4 guys to do that because there's so much information, so much knowledge they need to have. So we're talking about many different teams working together. So microservices is the direction we took so that we can separate the focus of these teams. At the same time, at the end of the day, system kind of comes together. User experience, we'll focus on industry domain. We created a specific user tailored to the industrial space user experience and different patterns, different tools around user experience so that you no longer have to create your own experience or come up with something, spend so much time and research doing that. There's easy to use things already built. DevOps, it's a natural software development nowadays. You need to be able to get new versions quickly. There's lots of talks about monolith versus microservices architecture, but the premises of the microservice, if you want to fully take advantage of that, you need to have the automated automation. So CI/CD pipeline has to be automated. Otherwise, it's too much to handle. Infrastructure is going to be too big very, very quickly, and it will be really hard to manage. Security has to be looked at not only from the software point of view. A lot of people think about security, how do I get my credentials? How can I log into my portal and be able to access data, right? But security doesn't stop there. We need to look at the holistic picture. All the way from the hardware, when I show the spectrum, like hardware, security built into the hardware extends all the way to the cloud elastic system. Anything in between also has to be secured. And Michelangelo will talk more about the how we're doing there. And then legacy. Don't forget that this industry is a lot of assets in the industry are very old, 20-year-old, 15-year-old assets. They're not going to go away anytime soon. Somehow, we need to integrate that legacy into modern system, right? How do we do that? We need to design our platform so that its integration is built in. Okay, there's lots of hooks. And I leave the edge for Michelangelo to talk about that side. Let me quickly kind of show you high-level reference architecture. So in order to build a truly industrial platform, you have to look at the use cases. So this is what we did. We looked at multiple industries: aviation, healthcare, transportation, oil and gas, manufacturing, power, and such. So look at the use cases in those industries, found some commonalities. What problems people trying to solve? So now, based on those commonalities, we created a cloud side with different layers, if you will, and then we created the edge side. Okay? So now, again, this is a high-level picture, but I want to focus a little bit on the cloud side, just to open up a little bit more. So we have hardware infrastructure. Then you have infrastructure as a service, so that we can create on demand different VMs, so we can put some software on it. On top of that, what we want to do is create microservices runtime environments, which in our case, we're using open source software Cloud Foundry to host the microservices and manage them. But also, some of the applications could go into a different type of microservice runtime, which is based on the containers, Docker container, for example. But don't forget about legacy. So where's your legacy going to go? Okay? For that, we can have some VMs that basically can host the legacy applications. And now you see we have the modern software that we can start from scratch based on microservice concept. We can bring some mix of modern and existing software, and then legacy. So everything kind of blends together if you put this layer called API Gateway, which connects all of these three environments and offers a set of services to build applications. So on top of that, you're building applications for a specific industry. Okay? So again, this is high-level picture. If you have more questions, we can take the questions in our special session, I think the office hours tomorrow. So now, challenges. Let me talk a little bit about challenges. So GE started focusing on digital heavily about 4+ years ago. We started from almost 0 software developer in GE digital side, and grew in 4+ years into over 1,000 software engineers. Okay, that's a huge challenge. Not only building the software, but also building the organization that is capable of building industrial-grade software. So we had legacy SDK-based software stack that basically would be offered to internal GE customers as a package, as a tool set that they would take and build their applications and host it themselves. Okay? That we turn into a cloud-hosted platform. From the legacy, take everything, pull it apart, create microservices, put it in the cloud. We use design patterns, of course, try to look into what makes sense. What kind of design patterns make sense for us? So we'll look at a number of those. For example, aggregator pattern, proxy pattern, circuit breaker, and such. And then looked really carefully about the API design. Because if you look at the modern websites, they have specific conventions around, okay, how do you properly design your RESTful APIs? So we'll look at the best practices and adopted some of them and now distributing to the team so that everybody is using those guidelines. Of course, standards and governance is key there so that everybody's disciplined and doing the right thing. So development, as I mentioned, from 0 developers to 1,000+ developers, having the sort of Scrum, waterfall combination of the process, going into pair programming, going into a little bit more pure Scrum teams, and distributing teams. Going from Java into multiple languages, and then using best practices. 12-factor app is one of the best practices we use. There's many others. If you didn't go to Matt Mamon's session on 12-factor, you can check the recording later. And then DevOps. As I already mentioned, DevOps is the key. Without it, there will be no fresh updates of software. Everything will be so slow. Everything will be faulty. So that's a critical piece. So if you want to check out what the platform has today, you go to predix.io and you have a free trial in there. So at this point, I'm going to hand over to Michelangelo. He's going to talk about the edge side.
Can you guys hear me? OK. So Michelangelo Russo, I'm with Alisher, one of the architects that is working on the Predix platform. We're going to talk about the edge, which, as Alisher pointed out, is whatever is not on the cloud. And we're going to touch briefly about security in the end. So the edge is what we deploy on premise, premise being where our assets are. So what are the challenges that we see in an environment like that? We've been briefly touching through the first part of this presentation. We had few items touched upon during the Statoil talk this morning. First of all, in an industrial deployment, we do have quite often a tight coupling between hardware and software. When we talk about system deployed on premises, we talk about embedded capability, so firmware, control software. Well, all these items working together. And what we have really is a set of bespoke solutions built by a provider or for a provider. And in this case, the challenge is how do we update these components from a software perspective when we cannot update with the same rate the hardware that is hosting that software. We have a challenge in the interoperability between systems. Yes, standards do exist. Yes, vendors do comply with the standards. Yes, sooner or later, every vendor deploys its own protocol, its own way of doing things, either because of protection of market share or because of optimization of performances. So between the components of the same vendors. So when we have multiple vendors in a plant, for example, and that is actually the norm, interoperability between items is a challenge. Hardware capabilities in terms of computational performances are growing. Still, we are far from the cloud. And at the same time, we talked about coupling between hardware and software at the beginning. And if we merge this with the average age of an industrial asset that this item have to live with, we do realize that quite often the hardware that we can find on the field is not exactly the most performing one. Obsolescence is a fact that is challenging us in deploying software. Finally, we do have, as I said, we can have multiple items coming from multiple vendors interacting into the same system. So, which means that beside interoperability, we need to take care of manageability of different solutions. Again, this is a challenge that we have. How do we deal, or how did we try to deal with all of this? We came with the conclusion that a platform must be, number one, as agnostic as possible with the supporting layer, starting from the OS down to the hardware, basically. So we started in Java, build once, deploy it everywhere. With time, we are kind of moving and exploring other possibilities about containers. For example, we know that containers as they are today do dictate the operating system. The catch there, the trade-off, is about the fact that we do have a wide pool of developers that in many cases are not even exactly software developers, subject matter experts that can code well, not only in Java, in C, Python, MATLAB, whatever they can think of. So the idea is to widen the pool of developers and make the system available to them. We are confident that the solution, well, the community behind the container is going to assess the defect of the solution as it is today. We need to be capable to scale down in footprint. An example of a hardware reference architecture that we have is 512 megabytes of RAM with 700 megahertz of processing power. A Raspberry Pi. If any of you have been playing with that, pretty much a Raspberry Pi. We need to be capable of deploying on something like that. So we need a platform on the edge that is capable of being scaled down. Our limit at the moment is around 10 megabytes. We want the platform to be pluggable. Means that if somebody wants to deploy a new release of a feature, of a new feature entirely, there is no redesign intended for the whole hosting environment. Service-oriented architecture is the way that helps us in there. Finally, we're building a platform, so a set of tools. A good platform comes with pre-baked solutions or options for customers. We cannot contain the total span of possible solutions, so we need the platform to be customizable by customers, and that's why we provided it with an SDK. Separation of concern is important between real-time and non-real-time software. There is a controller which is running the asset. The asset is generating power for a hospital. We don't want to mess up with that. So what we do is we enforce a hard separation between environments. 4 minutes. I got it. With something like this. Bottom up, the edge device, which is our hardware layer, a hypervisor, which might or might not be there, a real-time operating system layer, which is hosting the real-time control logic, and on your left, the non-real-time control logic, which is basically our edge platform, a core module, including capability like logging, troubleshooting, a set of services that take care of connectivity between machine, cloud, and humans, data management like persistence, device management, as well as the possibility to deploy on the side with this other applications, for example, as containers. And in that case, we take care of the connectivity between the core module and the external module. Now, we'll have to be quick, and so I'll move on the security quickly. But of course, I'm open for question about everything that is up here. Security, caveat, this is not a session about security. A session about security would be 1.5 hours on its own. So definitely, it's just a couple of items. Challenges are difference in paradigms. On the asset, on the edge, on premise, everything is theoretically fenced. So you limit the access of your stuff. You control who accesses what. Cloud is about sharing services, so things are different. The control of the full stack from the hardware to the software is not always possible. We cannot always dictate the operating system, the hardware, so we have limitations in there. Finally, yes, we have stuff in the field which has been out there for 15 years. We have protocols like Modbus, serial protocol built in 1979, still going hard in the field. So it's there, and we need to take care of that. So, concepts. Security is a holistic story. It's component. It's made by different components. Security ensured on a single component is not enough. As an example, we have the fact that our communications from the device to the cloud, as well as to the assets, are initiated by the device. We implement secure protocols like HTTPS, but also we have no opening listening port by default on our edge devices. We should prefer certificate-based authentication to username and password because devices cannot really log in. I mean, it's hard for them. Airtight isolation is an illusion. Everybody here knows about Stuxnet? Heard about Stuxnet? Yes. Stuxnet was a worm, a virus, deployed successfully on PLCs, industrial controller, on a nuclear power plant in Iran. Virus, nuclear power plant in the same statement. It's okay to be scared. This thing happened, and was an airtight environment, so that's not enough. Things need to be more detailed than that. The idea is to have a security which is integrated from the hardware up. I have a 0 in front of me, so I'll have to be awfully quick in this. Trusted computing, access control, secure communication, network security. And federation of concerns. Again, a shared network between items is a single point of vulnerability. Federating items in the network means that if you hit one of them, the other one can run. Those are the kind of 3 takeaways that we would like you to bring with you after this session. I'm sorry if I had to be quick on the final part. We are open for office hours on Thursday, both of us in the morning. I don't know if we have time for anything now, so I'll leave it to, but that's basically our last line. So.
Okay, thank you.